All right, gentlemen, are you present?
I think so.
Oh, I'm very distracted right now. Gerald? Hello, Gerald.
Still trying.
We're having
What's that noise out there?
oh yeah, well, at least we can hear each other now.
Yeah.
So things have improved. We're having a lot of technical challenges tonight, everyone, and we have a loud party out on the deck. So we're going to try to hear our own thinking as we speak. Don't ask us anything too complicated, please, and we'll see how we do. So I'm Richard, and I'm here with Gerald McKeegan and John Curry, and welcome to Virtual Telescope. And tonight we're with the 36-inch reflecting telescope at the Chabot Space and Science Center, fondly known as Nellie. And we have pretty decent clear skies. The smoke has cleared quite a bit. And we're very fortunate not to be socked in like the rest of California is. So we'll try to take advantage of it to the best of our ability and show you some neat stuff in the sky. I do want to remind people that, ironically, that the Chabot Space and Science Center is still closed, even though you hear all of this loud music in the background. It is open for private parties, of which there is one on the deck tonight, but to the public, it's still closed. So we depend on your donations and your community support. I want to thank the Fremont Bank for their ongoing support for our program, and everybody who has maintained their memberships and donations over the last now almost couple of years, right? Well, really a year and a half of the COVID-19. So we're planning on opening in November again, and we hope to see you up here when we reopen. And we hope everyone is staying well and making the most of their summer as it is. And I guess that's it. What am I missing, Harold? I know what I'm missing.
Well, I know what you're missing.
Yeah.
Sooner or later, this party outside the door here, they're going to start playing the chicken dance, and we're going to have to stop when they do the chicken dance, and we'll all have to get up there. You know,
we all have to run outside and join the chicken dance.
Well, I jokingly said earlier in an email that the skies weren't looking very good tonight, so we're going to have to do interpretive dance. I did not realize that I was so close to the truth. So hopefully it won't come to that, because it's really not something anybody wants to see.
So did you mention Fremont Bank?
I did mention Fremont.
Okay,
Bank,
good.
But we do have to mention the time change for next week.
Yeah.
It might be good to start with that presentation. So I'm going to turn it over to you and John, because you also wanted to talk about the relative nightfall throughout the year and why we're having to move our times around.
Yeah. So it's getting, the nights are getting longer and the days are getting shorter, and we're reaching the point where the nights are long enough to where we can start at 9 o'clock instead of 9:30. So beginning next week, Saturday the 14th, we will be starting our virtual telescope program at 9 o'clock instead of 9:30. So we'll run from 9 o'clock until 10 o'clock or so. So you want to be sure to tune in then. And if you wait till 9:30, you'll miss half the program. And it's probably going to be the better half of the program. So 9 o'clock next Saturday, August 14th. Of course, you know that the length of the day changes throughout the year. In the summer, we have long days and short nights. In the winter, we have short days and long nights. And we're sort of in the transition from the short nights to the long nights. And of course, that makes all us astronomers happy because, you know, we do it in the dark and we like as much darkness as we can get. So stay tuned next week for at 9 o'clock instead of 9:30. All right. All right, Sorry, Richard, you were muted there.
I was, because I figured I should have as little audio as possible because of the loud music.
Well, everybody's listening for the chicken dance now, you know.
That's right. Or they're looking it up on Google.
Yeah.
Don't know what it is.
You missed the Macarenas in the dance, but now
you already missed that. I'll remind everybody again before we close tonight that we're starting at 9.
Okay. Richard, I've got the telescope pointed at Alberio right now, so why don't we switch to your live view and check out a couple of stars.
Get that to work here. Stand by. And let's share my screen.
So we're using our 36-inch reflecting telescope, the one we call Nellie. And Nellie is a reflector, so it uses mirrors instead of lenses. And it's got a primary mirror that's 36 inches in diameter. So that's the telescope we're using. It's our most powerful telescope here. Unfortunately, it's the one with what happened?
That's a good question. Did it move? Yeah, there we go. Thank you.
All right.
I thought it was me, but it wasn't.
It was me. I pushed the wrong button. I've been known to do that.
It was either that or you sat on the hand paddle.
Yeah. All right. Well, focus looks pretty good. So this is an object which to the naked eye looks like one star, and not a particularly bright star either. If you look at it with your naked eye here in the Bay Area, you might have trouble seeing it, although it's really easy to see when you get away from the city lights a little bit. It's called Alberio. It's the second brightest star in the constellation Cygnus, the Swan. And to the naked eye, it looks like one star, but when we look at it with our telescopes, we see that there are actually two stars here. And if you look carefully, you'll see that they are not the same. Sorry about that. They are not the same color. So one of them is kind of a golden yellow color, and the other one is kind of a bluish white color. Star colors tell us the temperature of the stars. So if a star is very hot, it'll be bluish. And if a star is cooler, it'll be yellow. And if it's cooler still, it'll be orange. And if it's a really cool star, it'll be red. So looking at these two stars, you can tell the one on the right, the yellow one, that's the cooler of the two stars. It's the yellow one. And then the blue one on the left is the hotter of the two stars. Now you notice that the yellow one is brighter. And that may fool you into thinking that that star is closer to us than the fainter star. It's actually the opposite. These two stars, the closer of the two is about 387 light years away, and we're not sure of the exact distance to the other one. It's somewhere around 7 or 8 light years farther away. But the reason the yellow one looks brighter is because it's bigger. Even though it's cooler in temperature, it is much bigger in size. It's a star that's approaching the end of its life. And as stars approach the end of their life, they swell up and they get much larger, and that gives them more surface area to radiate light. So even as they are cooling, they are also getting brighter because they have more surface area. So the yellow star is actually the more distant of the two stars. All right, and again, this is called Alberio. And although it looks like two stars orbiting each other, we're pretty certain that they're actually too far apart to be orbiting. There's still a little bit of debate among astronomers, but the more data we get, the more it looks like they're much too far apart to be orbiting each other. They just happen to be in the same line of sight. All right.
Margot pointed out that these are Cal colors.
Yeah,
that's right.
And we've mentioned that in the past.
Yeah, in fact, it's actually been called the Cal star many times.
the Cal Star, the Berkeley double.
Did you want to take the time to visit any more doubles in Cygnus? Cygnus is chock full of bright double
Yeah,
stars.
there's actually a lot in Cygnus. So
Yeah, I did mention
you
that.
got another one you want to go to?
Well, we have both 16 or 61 Cygni, and they're both similar doubles, at least according to our chart, in terms of the distance from one another, or apparent distance from one another. So,
Well, hang on a sec. You say 16 Cygni?
yes.
All right, well, let me try that again. Maybe I misspelled it.
Let's see. I may have to give you an SAO number or something, huh?
Well, maybe it doesn't like the Cygni part. No, there we go. Okay, I got it.
Find it? Okay.
Yep, I got it. All right, here we go. It's on the other side of Cygnus.
There we go.
Yeah, so Alberio is right at the head or the beak of Cygnus, and this is, I'm guessing, near the back end of Cygnus. Yeah, almost near.
Out on one of the wings.
Denton. Oh, it's out
Yeah.
on one of the wings. Okay.
Yeah.
Well, there you go. So these are very similar stars to one another. They're not very different with respect to their spectral class, but you can see that they're a very similar distance as the two stars in Alberio were. So what a lot of people don't realize is that at least half, if not more, of the stars you see in the sky are actually double stars. The double stars are very, very common. It's not this, rare event. It's just when stars condense from hydrogen and from their what's called molecular clouds, they often do so in pairs. And then they end up orbiting one another, and they live out their lives in orbit around one another. This kind of gives you an idea that there's plenty of them to see. Nothing much to say about these except they're a lot closer than Alberio. This is a much closer pair.
So do you know if they are orbiting each other?
Yeah, these are also in orbit around one another.
Okay.
And the other one was 61. Want to take a look and see what that one looks like. Probably should have done that one second and this one third, huh? And these are considered K dwarf stars. And I don't know if you can remember what the last ones looked like. They had somewhat different color. These are more on the yellow side. We lost your audio.
Yeah, I'm mute. Give a little more color here.
You scared me. I thought we were having our technical problems again.
No.
All right.
I was just testing you.
All right. So this is a pair of what are called K-type dwarf stars, and the orbit is every 659 years. So it takes a while for these two to go around one another. You could see that this is a double just by using binoculars. They're bright enough. It's magnitude 5 and magnitude 6.
How are they on distance?
They have
to be closer than Alberio.
They're very close, relatively speaking, 11 light years.
Oh, yeah, okay. Gee, that's our backyard.
It's nicknamed the Flying Star, and I'm trying to find out why. It has a very high proper motion. Okay, that's why. So even though it has a very long orbit, when observed from Earth, we're able to see that motion very clearly because of how close this pair is. And we're able to see, as the Earth goes around the sun, we're able to take precise measurements of where these stars are in relation to the stars in the background. And we're able to very carefully measure and calculate these orbits. So anyway, because of the unusual motion across the sky of these two stars orbiting one another, they're nicknamed the flying star.
If we happen to know it, Stephen wants to know the size of these two stars relative to the sun, or the mass.
That's a good question. I don't know much about K-type dwarf stars, Gerald. Do you have any?
They're lower mass than our sun. They can be as little as half the mass of our sun. They're cooler in temperature. They're about 500 to 1,000 degrees cooler in temperature. Which was the full classification? So K1, K1, K2, something like that.
Yeah, I think it was K2, but I'd have to go back and look. Give me a sec.
What stars are we talking about?
61 Cygni. And K-type, blah, blah, blah. Where is it?
I think there's something else about 61 Cygni that's kind of important. I believe that's where the first exoplanet was discovered. I may be wrong, but that sort of rings a bell somewhere in the back of my head.
I thought it was that was an Eridanus, but that's okay. I don't know. Maybe you're right on that. So the other interesting thing about this is the fourth closest star or set of stars to Earth that you could observe with the naked eye, which is just an odd piece of trivia.
So you can see Sirius is a little over 8 light years away, and Alpha Centauri. So this is the sixth, did you say?
Fourth.
Fourth. So Alpha Centauri, Proxima Centauri. Yeah.
There is, let me see. On different occasions, it's been claimed that 61 Cygni may have unseen low-mass companions, planets, or a brown dwarf. And that first claim was made in 1942. I almost said 1492. 1942. I'm a little dyslexic. And there are perturbations in the motion of one of the stars, at least, that suggests that there's a third body of about 16 Jupiter masses. So I don't know.
Cool.
But none of that's been proven. So I don't see anything about planet discoveries here in this article.
Okay, for some reason, 61 Cygni rings a bell with me for some reason.
It does for me as well, but I don't know if that's what the reason is.
All right. Well, let's move on.
All right. So much for that. All right. So, Bob Schock was saying we should try to look at the Saturn Nebula. And it might be clear enough to actually pull that off. And I believe it's NGC 6934, and I need to look up where that is. Let me see. NGC 6934. No, that's not it. That's something different. Hold on. He's confusing me intentionally. The Saturn Nebula. Oh, that's in Aquarius. So that's a little bit.
Oh, that's down low.
Yeah, we can't do that, Bob. Sorry.
At least not now. We can a little bit later on, right?
Yeah, and 6934 is in Delphinus, and that's kind of far from where we are too. So, not as bad, but
as long as we're in the neighborhood, we might as well check out. Speaking of nebula, the Ring Nebula.
Yeah, let's go over there. That's good. Right. That's always a fan favorite.
Yeah. All right, here we go.
We got word that they did have trouble with the Ring Nebula last night, but it is a lot clearer tonight than last night, so we might be lucky.
Margot asked if 61 Cygni was the first star that they calculated distance to. I don't think so. I think that was Alpha Centauri.
No, I think she's right.
Is that what it was? Maybe that's what it was. That was sticking in our memory here. Huh. I think you might have stumped us, Margot. Hold on. First star. Distance. First person. It was 61 Cygni.
I knew there was a reason that was bouncing around in my head.
Yeah, the first person to succeed at measuring the distance to a star using parallax, and I remember talking about the parallax a few moments ago, was F.W. Bessel, who in 1838 measured the parallax angle of 61 Cygni as 0.28 arc seconds, which gave a distance of 3.57 parsecs. And the nearest star, Proxima Centauri, has a parallax of 0.77 arc seconds, giving a distance of 1.3 parsecs.
You know what?
You're absolutely right. Thank you.
As long as we're talking about parallax and parsecs and all that good stuff, maybe a little later on, I'll explain how we measure distance.
That's a good idea. Yeah.
I've got a little PowerPoint that folks might enjoy. Okay, what's next?
Oh, okay. You were going to do the Ring Nebula.
We're on the Ring Nebula. Yeah.
Well, wait, maybe I should show it in the camera.
Maybe you should do an exposure and
take a picture.
Do something like that instead of just talking here. Okay, stand by.
So while Richard is fumbling around there, getting his camera. The Ring Nebula is one of many objects we call planetary nebulae. Planetary nebula is the remnant of a dying star. So these are stars that were once similar in mass to our sun, but they got old. When they get old, they swell up, they become red giants. The red giant star begins to blow its outer layers off out into space because of the radiation, the internal radiation, and the fact that when they're a giant star, the gravitational hold on its outer layers is not as strong. So it creates these winds that blow the outer layers of gas out into space. Looks like our aim is off a little bit here.
Yeah, but it looks pretty good.
Not far off. It looks like you got a good image, yes.
Yeah, I think so. If you want to move it a little bit before I take the next exposure.
Yeah, are you zoomed in?
No, I'm not zoomed in.
Okay, all right. So I'll move it a little bit here, and you can try again. So anyway, these old stars become red giants. They blow their outer layers of gas off, but this doesn't happen in an explosion. It's a slow process. It can take 100,000 years. And in that time, the star can lose half of its mass or more. And eventually what happens is you expose the hot inner core of the star, and then eventually the fusion process at the very center of the star stops. The source of that internal pressure goes away when the fusion stops, and so gravity takes over, the star collapses and becomes a white dwarf. And a white dwarf is extremely hot because it's taken what was a hot core and compressed it down even smaller. So it's very hot, it's very dense. The matter is what we call degenerate matter. So the electrons can't move around the way they want to, and that makes it very heavy. So if you took a teaspoon of a white dwarf, it'd weigh about as much as a Mack truck. So that is the white dwarf. The white dwarf is surrounded by all the gas that was expelled by the star when it was a red giant. The white dwarf is emitting ultraviolet radiation. Ultraviolet radiation can excite the atoms in the gas or ionize the atoms in the gas and causes it to glow. And so that glowing ring that you see is all the gas that was expelled by the the star when it was a red giant. And if you look carefully in this image, you can see the little dot right in the center. That's the white dwarf. That's all that's left of a star that was about 2,300 light years away, and it was probably very similar to our sun. So if you notice the color, it has kind of a turquoise green color to it, or turquoise blue, depending on your preference. That tells us a little bit about the composition of that cloud of gas and dust. Most of that cloud is actually hydrogen, and when you ionize hydrogen, it glows in a very soft, deep red color. And although there's a lot of hydrogen, in fact, it's mostly hydrogen, because it's not a very bright red color, it can easily be overwhelmed by other colors. So also in that cloud is oxygen, and it's ionized, what we call doubly ionized oxygen. And doubly ionized oxygen, when it gets that way, it will emit a turquoise blue or turquoise green color that's extremely bright, much brighter than the red color of the hydrogen. So even though there's a lot more hydrogen there, it's the oxygen that glows brighter. So it tends to dominate. So you don't want to be fooled into thinking there's more oxygen there than hydrogen. That's not the case. It's just that the oxygen glows a lot brighter than the hydrogen does. So what's going to happen is, over time, this cloud of gas is going to expand away from the white dwarf. Eventually, it will dissipate into space, leaving behind just the white dwarf. The white dwarf, there's fusion is no longer going on inside the star, so it's just this really hot lump of matter. And over very long periods of time, billions of years, it will cool, and it will eventually become a black dwarf. And a black dwarf is just a cold, dead lump of matter out in space. It's not the same as a black hole. Black dwarf is just the final stage of the white dwarf's existence.
Gerald?
Yes.
I think you're the first person to ever give an in-depth discussion of Planetary Nebula with the sound of Bohemian Rhapsody in the background.
Wait till they start playing Pink Floyd.
Well, that'll be that. You will not be the first. But
that's true. That's true. Okay.
All right.
I wonder if they can do the Beatles.
You'd have to do a special request.
Yeah. All right.
Only if it's from the White Album.
Yeah. Okay. Jeez. So where should we go from here?
We could take a look at some globular clusters if you want.
All right.
We have several choices.
Yeah.
I was
a
thinking
couple of nearby ones. Yeah.
Yeah, we could do a nearby one. We could also do M4 or M22 if you're interested.
That's heading south. Why don't we do M13?
Okay.
We'll do M13 and then head on south to M4.
All right. Sounds good.
All right. All right. Here we go to M13. I wonder if people can hear the music.
I don't know if they can or not. If you guys are able to hear the music in the background,
yeah, tell us. Yeah, we're kind of curious.
We're really curious.
We can't tell because we can hear it live, so
we can't even hear ourselves think right now.
Yeah.
I mean, this is like really loud, but I don't know if you guys can hear it or not.
It's not as loud as the Grateful Dead concert I went to way back a long time ago.
Gerald, you're leaking. You're sending your.
Yeah, I know. Giving away my age.
I spent many a lost weekend at a Grateful Dead concert.
Alan says not too much, so I guess maybe it
okay.
isn't that bad.
No, that's good.
So it's much harder on us than it is on everybody else.
Okay, well, that's good.
Are we there? Are we there?
We should be there. Yes, we should be there.
All right. I'm gonna bring the exposure down to 20 seconds, and let's see what we got.
Melissa's asking, are there any red dwarfs in sight?
Oh gosh, probably a bunch of them out there.
Probably a bunch of them, but
Yeah.
The thing about red dwarfs is that they tend to be very dim.
Very tiny specks in our images and barely show up.
Yep.
And they're red.
And they're very red, yes.
But maybe we'll make an intermediate stop at.
Okay, so we're off by a little bit, but it looks great. If we can shift over.
Are you not zoomed in?
I'm not. No.
Okay, hang on.
We're all the way out.
Okay. All right, try it again. So what we're trying to get here is called M13. It's also known as the Great Hercules Globular Cluster. Globular clusters are like balls of stars out in space. This one has about 500,000 stars in it. It's about 25,000 light years away. The stars in the cluster orbit around the center of the cluster, and the cluster orbits around our galaxy.
Hey, so in the meantime, while we're looking at that, Larry asks, is gravity making our Earth smaller? Is it smaller today than it was 2,000 years ago? Well, first off, 2,000 years ago is not very
really
far in the past. It's not very distant past. It's pretty close. But I don't know. Can you answer that, Gerald? Is it much smaller?
I don't know of anybody that's actually done any work on that, especially recently. I would think if you're talking about 4 billion years ago, it was getting larger because it was undergoing a heavy bombardment. But whether it's shrinking now, I guess plate tectonics may be due to slow shrinkage of the core as it cools. So it could be getting a little bit smaller, but don't quote me on that.
We don't have any numbers on that. So
yeah, it's a great question.
Yeah, there's no truth to the rumor that if we don't know the answer, we make one up. So
but we won't deny it either.
Yeah.
Yeah, that's not a bad view of M13 tonight.
Yeah.
Things a lot better than I thought it was going to be, and it looks good.
Stephen asks, is Alpha Centauri visible from Chabot? No, it is not.
No, it's the southern hemisphere.
Yep, a little too far south.
Yep. So I'm thinking maybe we'll go to what I think is a red dwarf star on our way down to M4 if you want to do that.
Yeah, that sounds like a great idea since we were asked.
Right.
Yeah, if you want to do that, I'll stop these exposures and we can
okay, go to
live view.
Yeah, go to live view, but it's going to be really dim if it shows up at all.
All right.
So.
Well, we'll see what happens.
All right. Tell me when you're ready.
Yeah, it'll take a few more seconds. All right. All right. Go for it.
Okay. Here we go. Okay, we're there.
Okay, I don't see it in live view, so let me try doing an exposure.
Maybe 10 seconds just to see what you get.
Whoops. Sorry about that. I don't want it to be looping, and we'll go to 10 seconds.
Speaking of Alpha Centauri, Alan mentions that it is visible in Chabot's planetarium. Yes, we can do lots of things with the planetarium.
Yeah, Alan's bragging about the planetarium because he spent so much time fixing it. Yeah, he spent 3 days. He did a lot of work on our planetarium projector.
Oh, do you
Yep,
think
I see it.
is it this one here, or is it this one here?
I think it's the one to the right.
Yeah. So let's move it. Move the scope a bit.
All right, I just moved it. Try again.
I'm gonna bring this down to 5 seconds.
Yeah, we have a Zeiss planetarium projector, which is a very complex instrument in our planetarium. It does a great job of projecting the stars. I mean, you feel like you're outside under the clear moonless night. But it does require maintenance, and Alan is our expert on taking care of those. And he spent 3 full days earlier this week doing that.
Gerald, why don't we try to get this more centered so we could sync the scope?
I just moved it.
Okay.
I just moved it. Shoot it again. See what you get.
It's looking pretty white there. I'm not sure that that's the red dwarf that we're looking for.
Well, the software shows it as a red dwarf, but okay. I won't swear to it.
All right. Well, so much for that.
Yeah. Well, that's a big disappointment.
Well, it's one step up from a black screen. So.
But what can you expect from the Three Stooges here?
Yeah, that's right. So we're gonna go for M4.
Yeah, we're gonna head that direction here. I want to try one other red star. Leave it in live mode if you want.
Will do.
I'm going to show her a red star if it kills me. All right, there's one.
Oh yeah, that one is.
Oh, that looks pretty red.
Let me get the exposure longer here. Yeah, it most certainly is. So what are we looking at, Gerald?
Guide star, Hubble Guide Star, GSC 981:764.
Wow.
My favorite star,
It was just on the tip of my tongue.
That's the one I thought it was.
All right. So, I guess the message here is red dwarf stars are not very bright. They're not very big. And so they're a little bit hard to see even with our big telescope. And there are a lot of them out there. For all of the stars that you see with your naked eye, if you go to the darkest location you can find, you might see 2,000 stars in the night sky at any one time. For all of those stars that you can see, there are at least as many and probably more red dwarf stars that are too faint, too cool in temperature to be seen with the naked eye. And they're out there. They are by far the most populous of all the stars out there. So, but yeah, this looks pretty good. You can see the orange color of it real nicely.
Mm-hmm. Tracy says, have we had a chance to view Mars? No, Mars is unfortunately a little bit too far to the west. It's set right after the sunset. So it wasn't even dark yet at the time that Mars.
Back in 2022. Okay, so let's see. I guess we'll go to M4.
Yeah, M4.
All right, hang on here.
You may want to do a sync before you do that.
I just synced on this one just now.
Oh, great. Okay.
All right, here we go. All the way down in Scorpius. All right, we are there.
All right, I'm going to need to switch
pretty low.
Yeah,
pretty low.
Give me a second, folks. I'm going to start exposure here. Let's see what we get.
Nicole says it's so dancey. It's dancey because of the live music that's playing. No, actually, it's because of the air motion in the sky.
Yeah, it's the live music. The stars are dancing to the live music.
Yeah.
Well, it could be shaking the telescope, so it is possible.
Are you doing an exposure? Because we're there.
Yeah, I am.
Okay. All right. Because all we're seeing is the same star.
I know. There it is.
There it is. All right. And we're off again.
Yep.
Why are you doing that, Richard?
I don't know. I can't resist.
He's just testing you, Gerald.
I guess. All right. Well, try it again.
All righty.
We are looking low in the sky, close to the southern horizon.
So things will be fuzzier.
Yeah, things will be fuzzier. We're looking through a lot more atmosphere. You'll hear astronomers sometimes use the term air mass, and that refers to how much of the atmosphere we have to look through in order to see an object. So if we're pointing the telescope straight up, we're looking through one air mass.
There we go.
But as we tip the telescope down, because we're now looking at an angle through the atmosphere, we have to look through more air. And the lower we go, the more air we're looking through. If we look at an object that's 30 degrees above the horizon, which this object is just about 30 degrees above the horizon, we're looking through twice as much air as when we're looking straight overhead. So air mass is pretty important. Actually, this object is 22 degrees above the horizon, so it's even more mass. Yeah, we got 2.75 air masses, so we're looking through a lot of air to see this. And that has several effects. One is it absorbs more of the light coming from this object, so some of the dimmer things in the object in this globular cluster don't show up so well. But the other thing is it refracts the light. That changes the colors and actually changes the apparent position in the sky. So it's one of the interesting things about looking at things at stars and planets and so on through the atmosphere is refraction of the atmosphere can actually change the apparent position relative to what we would see if we lived in a vacuum.
So I want to say a few things about M4, what we are looking at here.
All right.
So M4 is a globular cluster. There's various different types of star clusters, but globular clusters are characterized by having large numbers of stars in a fairly compact area. So we're talking about hundreds of thousands of stars in an area maybe 75 light years across. And in this case, M4 is about 75 light years across. And typically, a globular cluster consists of the oldest known stars in the universe. So we look at most globular clusters and we'll say, hey, those stars are, close to 13 billion years old, which is very close to the known age of the universe. And we're able to make that determination by looking at those stars' composition. And if the stars have what's called very low metallicity, basically consisting mainly of hydrogen without the heavier elements, then we're able to determine that they're part of a very old population of stars. Now, what's interesting about M4 is that it consists of two populations of stars. The old ones, like I talked about, but also a much newer population with a much higher metallicity. Basically, it's got a lot more iron and heavier elements in it. So it looks like that the cluster had two phases of star development, and it may have had something to do with, the gas clouds that formed this cluster. Perhaps they merged, or there was another event that catalyzed new star formation. So it's a little bit of a mystery on why this cluster is like that, but it is one of its unique characteristics. The other unique characteristic is this bar shape that you see right in the middle of the cluster going vertically through the center, and that's something that you could see through an amateur telescope. It's one of its characteristics that distinguishes it from other globulars in the sky, and you can see it pretty well magnified here. And I'm looking at a much more zoomed out image of it, and I think we can actually see it a lot better.
Yeah, this isn't a bad image.
Yeah.
And as somebody pointed out, there's a lot of yellow stars in it.
Yep.
These are all old stars, so we would expect to see a lot of yellow stars. So, Richard, it's about 1:15. We were talking a little while ago about parallax. I do have a little presentation that we can do about parallax and how we measure distances to stars.
Sure, I think
I can do that, and then we can go back to the telescope and look at a planet.
Yes.
All right.
Good idea. Okay.
Yeah.
I know what you're thinking.
We were asked about planets earlier.
Yep. So stay tuned, folks. We are going to. Okay, you got to enable me.
Oh, sorry. Let me do that. Give me a sec here.
Richard mentioned earlier that we had a lot of technical difficulties right before starting up tonight, so we apologize if we weren't quite ready for everything.
Yeah. Everything happened at once, and none of it was good.
Right.
So far, it's been pretty good.
Once we got started, it's been great.
Yeah,
so.
yeah. We were actually at one point thinking we were not going to be able to do the show tonight. So, okay, am I ready?
Yeah, you should be. Good.
All right. So let's see. Share the sound. I think this is it. Yeah, so let me get started here. He said, there we go. Okay, so we were talking a little while ago about parallax and how we measure the distances to stars. So if you imagine, the Earth orbiting around the sun, and there's some distant star like the one you see hopefully at the top of your screen here, we want to measure the distance to that star. To do that, for stars that are within a couple of hundred light years, we use a technique called parallax. And parallax is something that a lot of you, or I would think most of you, are pretty familiar with. It's actually how you estimate distances with your eyes. And what it simply boils down to is if you look at something in one direction, and measure the direction to it, and then you shift position and look at the same object again and measure the direction, you get two different angles, and using some trigonometry, you can estimate the distance to that object. So that's all that there is to parallax, but I'm going to kind of demonstrate. Imagine the sun down here, and here's the Earth in its orbit around the sun, and let's say today, we take a picture of this distant star. So we point the telescope at that star and we see it, and it's a star that's maybe 30 or 40 light years away.
Be aware that these angles are really exaggerated quite a bit.
You're getting ahead of me, John.
Okay.
So we measure where the star is relative to the background star. There are stars behind it that are 1,000 light years away. So we measure the position of the star relative to those very distant background stars. We can also measure it by just, what's the angle of our telescope pointing here on Earth at the star. So we come up with a measurement. Now, the Earth is orbiting around the sun, and it orbits in this direction. If we wait 6 months later, we're on the other side of the sun. And if we again measure the distance or the direction to that star, we get a different direction. So now we see the star against a different background of stars. And the difference between the two looks like this. We get two different angles. And to do parallax, one of the rules in astronomy is that we split the difference. So we split it, so we get the distance. So we're trying to calculate the distance to the star from the sun. So what we do after we split this angle, we end up with an angle. And in order to calculate the distance, we need one other piece of information. We need what's called a baseline. And we have a very nice baseline because we know the distance between the Earth and the Sun. It's about 150 million kilometers. So we have a baseline of 150 million kilometers. We have an angle that we've measured. And then using some fairly simple trigonometry, we can calculate the distance to this star. But that sounds simple, but it's not quite so simple. As John alluded to, the angles that we're measuring are very small. We measure angles normally here on Earth. Most of the time, we measure them in degrees, 360 degrees to a circle. 180 degrees means you've turned a half circle around. A quarter circle is 90 degrees, and so on and so forth. So, degrees sounds good, but these stars, even the closest stars, are so far away that a degree is way too much. We don't measure a degree. We measure much smaller units than a degree. So the next smaller unit is what we call a minute or an arc minute. And there are 60 arc minutes to a degree. But to measure distances to stars, even a minute is too big a unit of measure. So the next smaller unit is the second, or the arc second. There are 60 arc seconds in a minute, and there are 60 minutes in a degree. So you've got 3,600 arc seconds in a degree. So we're down to a pretty small angular measurement, but unfortunately, we're not small enough. Because of the stars are so far away, we have to measure even smaller angles. So just to kind of illustrate that point, suppose we measured the angle and it was 1.0 arc seconds. How far away does a star have to be to have a parallax angle of 1.0 arc seconds? And it turns out that that distance is what we call a parsec. It's 3.26156 light years away. And that's the distance that would give you a parallax angle of 1 arc second. But it turns out that even that is not enough. The closest star to us is a little over 1 parsec away. So its parallax angle is even less than an arc second. So we really need another unit of measure to get even smaller angles. And that unit of measure we use is called the Milli Arc Second. A Milli Arc Second is 1/1000th of an arc second. An arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So we're talking about really, really small angles. It's very difficult to measure these small angles, and it wasn't until well into the 19th century that anybody was able to actually measure the distance to a star using this parallax technique. But it does work. Today we have much better telescopes, much better capability of measuring parallax angles. So we've now used this technique to measure distances to a lot of stars. Hang on just a second. My virus software is trying to mess me up here. So we can now measure much smaller angles from Earth. And if we put a spacecraft in orbit around the Earth, out in space, you can measure even smaller angles still. So as a result, we're able to use this technique to measure stars out to several hundred light years away. So I wanted to go with my next slide here, just kind of show you the parallaxes of some familiar stars. Alpha Centauri, we talked about that earlier. That's the star that you see in the southern hemisphere. It's the closest star to the Earth. Sirius is the brightest star in our night sky. Vega is one of the stars that's in our sky right now. Arcturus is also in the sky right now. Regulus is a star that's in the constellation of Leo. Polaris is the North Star, and Betelgeuse is a bright star in the constellation of Orion. So here are the parallax angles, and these are all in milli arc seconds. One milli arc second, again, is 1/1000th of a arc second. And the cool thing about measuring in milli arc seconds or in arc seconds is that if you take the inverse, because one parsec is the distance that a star would be if it had a parallax angle of 1 arc second. All we got to do is take the parallax angle and take the inverse of it, and that gives us the distance in parsecs. So here are the distances to these different stars in parsecs. And as you can see, the smaller the parallax angle, the greater the distance in parsecs. So here we've got a big parallax angle and a very low parsec distance. And then down here, we've got a very small parallax angle, and the distance in parsecs is very high. Now, converting these to light years, these are the numbers we get, about 4.4 light years for Alpha Centauri, up to almost 720 light years for Betelgeuse. So once again, just to review, a parsec, it's a combination of the words parallax and second. We're measuring parallax, and a parsec is the distance that corresponds to 1 arc second of parallax. So that's what the term means. Its distance is in light years is 3.26156 light years. You'll be tested on that later. And keep in mind, this is really important now, it's a measure of distance, not time. That sec part, don't be fooled by that. That does not mean that it's a measure of time. It's a measure of distance. So, for example, should Han Solo be bragging about the Millennium Falcon and make some brag about how he made the Kessel Run in less than 12 parsecs? We, all of us astronomers, heard that, and we said, what the heck is he talking about? That's completely wrong. Parsec is not a measure of time. It's a measure of distance. So, you know, we always get a good laugh out of that, you know.
Laugh it up, fuzzball.
Oh, well, sorry. Excuse me. Sorry. You know, I got to give old Han Solo credit, you know. We're making the assumption that parsec for him means the same thing as it does for us. But you got to remember, Han Solo was around a long time ago in a galaxy far, far away, right? What's going on? Stop! We can't do this! Stop! My goodness, we're going to get kicked off of Facebook. So,
We're
all right.
Sued by Spielberg or something.
Yeah, there you go. All right, so that's my show. So I hope everybody understands now what a parsec is and what parallax angle is and how we use it to measure distances to stars. Now, once we've established the distances to stars within, say, a few hundred light years, there's a lot of stars out there. And there's so many stars that we actually can create quite a catalog of different types of stars, different temperature stars, different mass stars, different age stars. And since we are able to measure the distance, we can kind of put that all together in a model that lets us predict the distance to even more distant stars simply by measuring those other characteristics, their luminosity or how bright they are, or their temperature, or by looking at the density of the gas around it, we can estimate the age. Using all that information and plugging it into our model based on the nearby stars, we can estimate the distance to much farther away stars, thousands of light year away. So that's how we measure distances. All right. Okay.
Well,
Any questions?
Let's go to something much closer. Then.
I think we're there. Looks like we're there. We're there already. There we are. I guess so.
Richard, you're muted.
It's just as well. I didn't say anything important.
So here it is, the ringed planet, Saturn. So once again, it gets kind of low in the sky, so it's kind of not a nice clear image. We would like it to be higher up in the sky so we can actually see a lot more detail. We can see the rings, but we can't see detail within the rings. We can't really see any of the stripes on this planet itself, but we got Saturn.
Stephen was asking, how's the NASA addition to the Chabot Observatory going, and are we still reopening in November? That's the plan.
Yeah.
So, yeah, everything is going according to plan.
At least so far.
Yeah. Yes.
I am your father.
Yeah.
All right. Well, why don't we take some time to take some questions?
Yep. Yep. We'll leave you with this image and then answer questions for a while.
But what time is it here?
It's 10:30.
Is it?
Yeah.
Oh, you're right. It's 10:32.
So we can take a few questions if anybody's got any. If not, and of course the music just stopped.
Yeah.
Now we can actually hear ourselves.
Now we can hear ourselves think, so you could ask a hard question.
Yeah.
Yes, Bob, thank you. I was going to do, I promised, and if you hadn't reminded me, I would have forgotten. Next week, everyone, our program begins at 9 p.m. and not 9:30. So it's getting dark earlier, so we can start our program earlier, and 9 o'clock. So don't forget.
Yeah, somebody was asking a question about Jupiter. Jupiter is actually behind the dome. We have a dome that houses one of our other telescopes, and it's next to the observatory we are in. And right now, Jupiter is being blocked by that dome. But in about a month, maybe a little bit less, we should be able to see Jupiter and Saturn both on the same night.
Yeah, that'll be good.
Yeah. All right. Any other questions? Fire away.
I think that's it.
I think we've
lots of thank yous and stuff like that, but I don't see any.
And Lisa sent us 50 stars.
All right.
Are they red stars or are they?
All right. Well, thank you, everybody. Once again, I just want to remind you, we are still closed, so we still rely on your donations. So if you want to click on that donate button at the top of the Facebook page or somewhere on the Facebook page, or if you want to go to the Chabot website, chabotspace.org, and you'll see a donate button at the top of the page there. Help us out. We would certainly appreciate it. All right.
All right. Well, thank you, everyone.
Oh, we forgot. My goodness. Don't go away. Perseid meteor shower.
Oh, yes.
Yeah, so this coming Wednesday night, early Thursday morning, is the Perseid meteor shower. The Perseid meteor shower is caused by a stream of particles left behind by the comet 109P/Swift-Tuttle. And it's one of the better meteor showers of the year. We can expect to see 60 or 70 meteors from here at Chabot, and if you're in a really dark location, you might see as many as 100 meteors over the course of an hour. Best time to look is a little bit after midnight. Don't use binoculars, don't use a telescope, just lay back on the grass and look straight up into the sky and wait for a while, and you should be able to see a few meteors. And one of the cool things is we won't have a moon that night, so it'll be a great night to be viewing the meteors. So again, that's starting at about 11 o'clock on Wednesday the 11th and continuing until about 4 o'clock in the morning on the 12th. That's the best time to see it. But the meteor shower actually lasts several days. So even if you were to look the night before or the night after, you still should see a few. But if you want to see them at their maximum, it's the night of the 11th into the morning of the 12th, depending on where you live. So, all right.
All right.
Okay.
Well, good night, everyone.
Yeah.
And thank you for joining us tonight, and we'll see you next week.